Hello all, welcome back to the part C of lecture 11. In this part we are going to do some hands-on. So we are going to call and this hands-on will be based on R. So first we are going to read the CSV file. So we are going to read the German credit score data. So I have already shared this on the Google on the NPTEL platform. Credit. Also, if you do search German credit score data on internet, you will get this same data set. It's a slightly old but reasonably good data to get your hands dirty with, the first logistic regression model kind of thing. So yeah, if you just come see, there are about 1000 values and there are some status are given, and if you look into the status, if you go to and then the target here is good or bad, good loan or bad loan, and then essentially we have to, it is recorded as 1 or 2. So what we will do is data dollar good bad equal to, if we just say data dollar good bad -1, so that will give us, you see, good or bad. If it is 1, then it is bad, 0 means good, so we want to predict accordingly. Now if we just do summary of good or bad, so about 30% is bad actually. So just a minute, I think if I just do table instead of summary, if I just do a table, yeah, so 300 out of 1000 cases, they have 300 they have given as bad cases and 700 given as a good cases. Now typically in real life you will not have default more than 2-3% of the entire credit customers. So this is slightly artificial in that sense, because you cannot, if your 30% of customer is defaulting, then you will not be able to survive. But anyway, if you have in your data set, if you have only 2% ones and 98% zeros, those kind of data sets are called imbalanced data sets, and in those kind of data sets doing prediction is extremely difficult. Because most of the time what happens that any standard model will just say everybody is kind of good, then no matter what happens, 98% of the time you are correct, so and only 2% time you are wrong. So a naive model will be correct 98% of time. So so those kind of naive model we have to be very careful about. So what I will do first, I will just say number of rows in the data is 1000, I believe. Yeah, and then I will take aim is the testing number of testing, like n into 0.7, maybe 70% of the data we will consider for the testing. So 700 out of 1700 data points we will be considering for testing. So we will do a split the data into train and test. First what we will do, we will choose the train IDs, sample 1 each to n, out m many samples we will draw, and replace equal to false. Okay, we have to set up a seed. Set dot seed is 1 2 3 4. So the advantage of using seed is if you set up a seed and if you use exactly this number 1 2 3 4, actually you can do any number. I can just draw a sample between 1 each to 1000, one sample, and 913. Let me just use 913 as my seed. Now that means if you use this seed number as your seed, then what will happen is my result and your result will exactly match. Okay, so this ensures, because we are going to split the data set randomly, 70% data we will take as training data. Okay, so data underscore train equal to, what I'm going to do, data, just I will provide the training ID, comma, maybe I'll just do a sorting here. Okay, let me just take this and then I'll just data train and data test equal to, what I will do, I will just copy this, and instead of train ID I'll just say minus train ID. So just take all the IDs but don't take the training IDs. So that will automatically give me the testing data. And so row number 1, 7, 19, 20, 26, these came to the test data. And if you go to the training data, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, then 19 missing, 21. So those are the train data. Okay, so now we have splitted the data. So first we will fit a logistic regression using built-in function in R. Okay, first we will fit logistic regression using built-in function in R. Okay, now first fit GLM. So from the stats package you extract the GLM function, you call the GLM function. So you just say good, bad, and dollar. And I'm going to take two in this data. There are most of these data are categorical, but I just want to keep it little simple so that you understand it more easily. The duration in month is a sort of a numeric value, credit amount and duration in month. These are the two columns which are in numeric. There are some other numeric also, installment rate, present residence since, age. So these also can be, I can take, but just to, my purpose of this demo is to give you how the logistic regression works. Okay, you can add as many predictors as you want. There are about 19 or 20 predictors are there in this data set, but you can add as many predictors as you want. My purpose is to just give you how the whole logistic regression works in R. And what what I'm going to do, I'm just going to take two predictor which are numeric predictor, and what I'm going to do, I'm going to just scale this. Scale always helps. Duration in month and plus scale credit amount and then data equal to data train. And now here is the important part, that you have to mention family equal to binomial, because remember that it's a binary classification model, so it raised into binomial. Okay, I have to save it somewhere. Let me just call it so I'll just call it maybe MLE logistic regression. Okay, binomial. So since it is a binary classification problem, in the binary classification problem, the model automatically raise up what it comes is a binomial model or Bernoulli model. So, and we have to give a link equal to, we will say logit. You can use probit also. And let me run. It should be stats, not stat. Yeah. Okay, no error, means probably it has run well. Now I'm going to say summary fit GLM. Okay, so what it says that duration in month and credit amount, both of duration in month has a statistically significant effect in the whether a customer is going to be a good customer or bad customer. And turns out credit amount is not that important. You see, p value is very large, but credit amount is important. So this is the estimate, the coefficient. These are the standard error and z value. So you can have these, you can create these informations. And now what I'm going to do is, now we are going to pretend that as if GLM function in R does not exist, and we want to code it from scratch. Okay, so we are going to write down the negative log likelihood function, and then we will use the optimization subroutine technique, and we will find what estimates of the coefficients are, and whether these estimates are going to match with built-in GLM function. Okay, so first write negative log likelihood function. Okay, all right, let me just write a point here that now we pretend that GLM does not exist, and we want to code from scratch. Okay, now we want to code from scratch. Now first, how do you do that? Now negative log likelihood. You have to write the negative log likelihood function. So there will be all the statement will be inside, and then everything is first data set name we have to give, then beta values we have to give, then y name we have to give, and the x names we have to give. Correct? All right. So the first, from the we have to extract y from the DSN y name and keep it in x, and then x equal to scale DSN x name. So the way I'm doing it at this moment, it will not work for categorical variable, so it will work only for the numerical variable. But writing the full-blown code is not my purpose. My purpose is to give you a demo that how, if required, you can write your own model, you can develop your own model, write down the likelihood function, pass it through the optimization subroutine, and fit your own model, and hey, here is your own model. Isn't it fun? So what I'm going to do is, first is n1 is n row of DSN, and then I'm going to define it as, remember that most likely DSN is going to be a data frame. Not most likely, we are going to pass it as a data frame, but we need to do a matrix operation. Since we need to do a matrix operation, what we need to do, we have to call it as matrix, this x as dot matrix, and we have to do this cbind dot data dot frame with x, and before that intercept equal to replicate of 1 comma n1. So we have to create a x matrix with all the x columns that has name of the x columns with all the predictors name, and a column which will be intercept, right? Now then, once I have the x, what I have to do, I have to calculate for z. Remember that in the theory part we have a z value, latent variable z. So this is the latent variable I'm going to introduce here, percentage star percentage beta, and then p equal to e to the power z divided by 1 plus e to the power z. Now I have the p. Wonderful. Now what I have to do is, f equal to 0, I have to calculate the log likelihood. Actually I should say log likelihood, LL equal to 0 for, look, I could have done it slightly better way in some kind of, more computer efficient way, but my purpose is to show you not a write an extremely efficient way of writing the code, but my purpose to show you how the concept of writing negative log likelihood. And because the best thing is if I could have write this 3 lines of code in a vectorized form, but instead of writing it in a vectorized form, I'm purposefully writing it as in a loop, so that you can understand what I am doing. So plus, now y I times log pi plus 1 minus yi into log of 1 minus pi. Okay, now here is a task for you. Okay, write this code, 3 lines of code without for loop. Can you do that? And check if you do that, whether your overall optimization time is going to be reduced or not. So let me just finally write negative log likelihood will be just minus of log likelihood. So LLL, this is my log likelihood, and then return negative log likelihood. Okay, now once I have written the negative log likelihood, at least we have to check whether the value the function works for some data set or not. So some initial value, DSN will be data underscore train, then beta will be 0, 0, 0. So why 0, 0, 0? Because you see, I have in the model that I'm trying to fit, this model I'm going to fit. So intercept, one coefficient for duration in month, another coefficient for credit in amount. So these are 3 coefficients. For all 3 coefficients, I'm going to give initial value of 0. And then I have to give yname. Yname is in a vector form. Sorry, yname is good or bad. Good, bad, and xname. Actually, I can just copy these names, duration in month, because that is the name exactly what we have, and credit amount. Okay, so if I just run this, these are the initial values, these are going non-conformable. Let me see. Of course, because it should be Z. So there was a mistake. All right, let me run it once more. Yep. So in the first initial value, the negative log likelihood function runs and it gives me a value of the negative log likelihood. Now I am going to initiate the initial value of beta. I have to give initial value as 0, 0, 0. I have given here. Maybe I'll just run it here and I'll do it there. And if I just run it, yeah, it's working perfectly fine. And then I'm going to write optimization subroutine to get the maximum likelihood estimate. Write optimization, or just call optimization subroutine optimization to estimate MLE of beta. Okay, so what I will do, fit LR logistic regression with optim, and from the stats package you just call optim. Okay, the parameter first is you have to give the parameter, which is initialize beta dot init, Then you have to give the objective function. And what is your objective function? This is your objective function, negative log likelihood function. So you have to give the objective function. Then you have to give some additional. In the objective function you have ds data.train. Then in the objective function you have this yname and xname that you have to provide. Okay, so and if you run this, oopsie, I have made again a mistake. It should be stats, not stata, and it has run and without any error. So this is a good news. And let me run from this. Let me call the parameter estimated parameter value. So these are my estimated parameter values. So these are my parameter values from manually estimated, whereas when we use the summary.fit or maybe coefficients, we just call coefficient of fit glm. This is looks like these are exactly, not exactly, but at least up to 3 decimal places they're matching. Looks like 0791 0791. So up to 3 to 4 decimal places it is matching. 3 to 4 decimal places it is matching. There are ways to match it. If I increase the tolerance level and all these things, then it will match maybe up to a great extent. So what I will do, if you in fact, I can just say cbind and to just compare, you can see. So first one is from optim and second one is from the built-in. Yeah, so this is the, when we use optim, this is the value, and when we use the built-in R function glm, this is what happens. So they're almost matching up to the 3 decimal places, and then they're deviating. This one has matched up to 4 decimal places. 3 to 4 decimal places they are matching. If we increase the tolerance level, probably we will match even more. So now we have the, let us write the beta hat. So since, okay, so beta hat equal to fitlr par, and then x test we have to take from, we have to scale it. Remember that we have to scale it. Data test comma these two value. So we have to take the test. Okay, we got the test values, and then what I'm going to do is we are going to calculate this first, the latent variable z hat, which is x test percentage star percentage beta hat. Sorry, I have to call this guy, and then yeah, it is not conformable. So of course, because I have to do few more work in row of x test, and then I have to call x test equal to, you see I have done this line, right? So I have to do the same kind of lining arrangement here also, because that's not, x test directly is not my my call. So let me just run this, and now probably it will be fine. Yes, now it is fine. Now it is fine. And now once I have the z test, let me just have p hat equals to e to the power z hat divided by 1 plus e to the power z hat. Okay, so this is my p hat. Now now in the data test, I'm going to p hat equals to p hat. This is going to be a new column in the data test. See, I have created a new column here. All right. Next, what I'm going to do, I'm not sure why it shows a p hat column 1. Okay, we will see what can be done. All right. Next is we have to predict. So data test $good bad, but we have to do first prediction. The prediction equal to, first I'm saying 0, and then first I'm taking all the values of sort of a 0. Actually, what I can do, I can just take this, yeah, I'll see what I can do, and then I can just say that if p hat is greater than 1 or greater than half, then most likely it's going to be a bad customer. So there are some prediction where it has said it is going to be a bad customer. Okay, now I'm going to do a table I call accuracy actual equals to data test $good bad and predict equal to data test $good bad predicted values, and this is the case. So there are, out of about 212 cases where 202 plus 210, there are too many like bad customer is being missed and said that okay, these are good. So it looks like the model is predicting most of the cases are as good, 2000 out of 300 test cases. So in the test cases, test data set, data test, if I just do a simple table of data test comma good bad, there are about 210 cases are good and 90 cases are bad. Now on the other hand, if I just do a table of data test good bad, so 282 cases are saying that they are good and 18 cases they are saying bad. So this model is actually failing to failing to say who is good, who is bad. So one thing people do try to understand, that if I, in case of 0.5, if I increase it to say 0.3, and will it be helpful? So if you do that, say probably yes. Instead of 0.5, if you just reduce it, now you have just too many probably saying, or maybe 0.4. So you have this many cases. So if you have that, now you have kind of 90 cases. In actual cases, these are the actual. So 90 cases good, and now it is better, slightly better. You can try out with this cutoff marks, but the problem is another level. Problem is there are two type of error. One is truly there is a good cases which is being predicted as bad, and there are bad cases, actually bad cases, which is predicted as good. So this is like actual bad cases which is predicted as good, which is actually bad thing. You don't want this to happen. If you, as a bank manager, you're giving loan to somebody and he or she is not returning in the money, that is a really bad thing. That's a real loss. This error, on the other hand, for a bank where actually the person is good, but bank thought, okay, if they will be bad customer and you are not giving loan, so in that case it's going to be a real problem. So we are seeing in binary classification there are two kinds of problems. So, and one problem is typically called false positive, another called false negative. In statistical language, it's called type 1 error and type 2 error. So we are going to talk about that, which one is good and which one is bad. In the next lecture, we are going to talk about that. So for now, thank you very much.